Hello, everyone. Welcome to EROSS. They are online summer seminars. Now, BOSC, which is associated with EROSS, has passed, but we are still, let's say, an extended part of BOSC and still connected to the ER, the International Conference on Conceptual Modeling, that will happen in the first week of November. So please stay tuned and check the ER website for a number of very, very interesting things happening on that week. So in this series, so EROSS is this series of talks with world-class researchers in the areas of in areas which are important to conceptual modeling, right? Databases and logics and knowledge representation and philosophy and cognitive science and so on. In some of these talks, we went more practical. Sometimes we went very theoretical and philosophical. And today, what we're going to do is to see a connection between these two worlds. So the talk today is in the intersection when conceptual modeling meets database. So the intersection of these two worlds of more theoretical aspects of logics and conceptual modeling and databases. And our guest today is my co-conspirator, my partner in crime in this whole adventure of EROSS, Enrico Franconi. I'm very happy that he is here today as a speaker. Enrico is a professor of computer science at the Free University of Bolzano, where he founded and directs the Knowledge Representation and Database Group, which now has approximately 50 academic members. He has been working for more than 3 decades in computational logic and natural language semantics, conceptual modeling, and foundations of database, areas in which he has done seminal work. He's been a PI of many international projects and chaired many important international events, and has been a keynote speaker in many events, including in ER 2007. In addition to his academic work, he has an impressive record of technology transfer with a number of projects over the years with organizations such as Italia Telecom, France Telecom, the Italian Space Agency, ORM Solutions, and the European Space Agency. He's also contributed to the development of many very interesting computational tools, which are very important for conceptual modeling. For example, Quelo, which is an ontology-based precise query formulation system. iCOM, which was a very, very pioneering tool for supporting automated reasoning over conceptual schemas. And iCOM evolved into what is called ORMiE, which is a plugin for Microsoft Visual Studio, providing reasoning capabilities for information system design. And now this is ORMiE is financed by the European Space Agency. So Enrico is the ideal person to give this kind of talk because originally a theoretician, he's obsessed with practical problems. So I know few people who are completely not interested in fictional problems and obsessed with the complexities of the real world. So I'm very happy that we have him here today. So Enrico Franconi, welcome to EROSS.
Thank you, Giancarlo. I'm shocked by the introduction that you gave. It looks like the speaker today is a very interesting person. I don't know whether I'm up to the expectation that this introduction leads to. So let me just say what I wanted to say, which is my understanding along all these years of how conceptual modeling and knowledge representation techniques and ontologies, which was the field where I started my research work on, how this actually connects to what was the original motivation to do conceptual modeling, so which is information systems, databases. And this kind of connection has been always underestimated or understudied, and maybe Giancarlo is right when he says that I really want to see the connection with the real stuff. Database technology, and here I really mean relational database technology, SQL-based relational database technology, is something you cannot really play about. So it's there, and it's the standard, is occupies 80% of the business in IT in the world. So it's something that you cannot really make assumptions which are not true in the real application. So when you want to study how to extend database technology, you have to accept this database technology for what it is. And so when I started to look what was the actual connection formally and practically, in the sense practically, really, whenever I mean practically, I mean an approach which makes sense in practice, but which is well founded in theory, exactly like SQL technology. SQL is, well, as I told you, really widespread and universal and practical in the world, but is really grounded in logic, in first-order logic, in relational algebra, in domain independence, first-order logic. So its groundings is very solid, and so that you can actually prove that whatever you do makes sense, and you can really understand what is the formal meaning of whatever you're doing. So connecting knowledge representation with database technology really meant to look at the small details of what database technology, SQL technology, actually is. So, of course, we're talking about conceptual modeling. Actually, I also find quite interesting here. I copied the title of my talk from the web page, where modeling is spelled only with one L, is American style, but from now on, apart from the title, I always will spell it with two L, because I'm European. So, of course, I will start with the obvious of my understanding of what a conceptual schema is, and I will give a definition which to me simplifies the connection with databases. And so, but this definition is very general, and you will see, but it's really equivalent to what would be my definition of an ontology, which is, or a knowledge graph. So use the buzzword that you prefer nowadays. Well, then I will instantiate this idea to databases. So I will show you a very generic architecture. So nothing very fancy here, but I want you to show the context. And then I will go into examples of the various technical problems that you are going to find when you want to exploit this connection between conceptual schemas and databases. So I will first revise, according to my terminology, the classical database case. So how can we understand what people already are doing in databases with conceptual schemas, and what is the real meaning of that? And for doing this, at the end, I will need a notion which is rather new, which is the notion of Lossy transformation. And we will see that all the real advances that you may want to do on top of database technology for once you have a conceptual schema involve breaking this property of losslessness. And so we are going to look at this very remarkable frameworks, which are nonetheless lossy, in the sense they will lose some properties. In particular, they potentially could increase the complexity of query answering, which is something that dogmatically we don't want to do. So we want really to stay into the complexity of query answering, data complexity of query answering of SQL, so under log space. So we will study these two approaches, the D boxes and an extension of this, which are the A boxes, and then I will show you why this is bad news, complexity-wise, and how can we actually fix that. And here I will just give you some hints about current research, because I can't really go into any details at this point. So the custom slide on what is a conceptual schema. So a conceptual schema, to me, gives the semantic of a system. Namely, it introduces a vocabulary which I can understand, that the agent can understand. So I really, again, want to be very abstract. So for me, a conceptual schema is any vocabulary together with its semantics, and we'll show in a couple of lines what is what semantic is. But any vocabulary which its semantics that connects to an actual system. And the actual system may have a different vocabulary. So the whole point is that in order to understand some system, this may be an information system, a database, but more in general could be a software system, for example. I may need to describe this system using a vocabulary which is closer to whoever wants to use this system. This could be a human agent, a programmer, a final user, and a program via an API, or a query language. So whoever is going to interplay with this system needs to have a clarified vocabulary for that, which is not necessarily the one in which this system is implemented. And in a sense, we also can mention here the seminal idea of code of data independence. So, well, we have data which is actually a system that stores data, which actually stores the data in some very peculiar form, maybe B-trees or index form, but then I want to see this data with a different vocabulary, which is a vocabulary of the tables. And then you can go a step further. So you want really to generalize much more, because we know that also tables are very peculiar, because tables are organized in ways that may be optimal for runtime, optimization of query answering, or update, or transaction, or aggregation. Whatever need you have, you may have a different vocabulary that is actually used by the system, but this information is always the same. For a particular agent, this means always the same thing, independently on how it's actually stored. And in this sense, I call this the conceptual schema, the conceptual model of this information system. So it's a vocabulary understandable by the agent and need to interact with the system. And I use this sentence, which really recalls, I guess, the very first talk that we had at EROSS by Nicola Guarino. So what is an ontology? Is a formal conceptualization of a perspective. Okay, to me, this doesn't really say much. So I say this because to me, a conceptual schema, in the way I'm defining it now, can also be called an ontology, a logical theory, a knowledge base, a knowledge graph, a set of axioms. They all have the same properties. So they have a vocabulary, and they somehow constrain this vocabulary to specify exactly the meaning of these terms. Namely, it specifies exactly, and that's the whole point, all the various configurations that the system may have. And so this means that all the legal states of a particular system have to satisfy my constraints, and all the states that are satisfying the constraints are exactly the legal states of my system. And if this is the case, then we have the perfect ontology again, in the sense of Guarino. So the fact that we are capturing the intended model exactly with the model of my theory. Okay, I called an instance a particular configuration of the system. And of course, the legal instance is an instance which satisfies the constraint. So the state of the system that satisfies the constraint. And I always focus on finite instance. Okay, so if we now focus on database systems as the system at hand, of course, we will have conceptual schemas, which are these vocabularies with their own constraints, which really talk about the data I have in my database system. And of course, the legal instances of this set of constraints will be in one-to-one correspondence with the with the actual database, which are all the databases which are possible for that particular domain. Okay. So let me quickly go through this architecture idea. So as you know, since I want to focus on databases, or the system that I want to consider databases. So here I have my classical scheme of databases. So I have the conceptual schema, which is what I'm focusing now about, which is connected at the lower level with the logical schema, which is probably the set of tables where the databases will be stored. But again, the set of tables is actually just an abstraction over the actual physical store of my data. The conceptual schema actually call this set of constraints, and you will see by examples this in a while. But this is exactly what we mean. So when I have an AR schema, an entity relationship schema, or an UML schema, or an ORM schema, or a set of OCL constraints, whatever. So they actually are saying that the data they will ever store in my database will have to satisfy these constraints. And what is nice is that when I design the schema, I will do it by looking at the domain information, the domain structure. And then later on, I will somehow translate the schema into the logical schema in a way that the logical schema will be structured with a different vocabulary, which will probably be optimized with respect to the query load, for example. But it could be also the other way around. I may start to have a logical schema, and then this will be reverse engineered into a conceptual schema. So I have a very complex database with many tables which I cannot understand, but I can actually abstract this and show the conceptualization of it by some conceptual modeling language. Could be OWL or ORM again, whatever. Okay, so what do we do normally in a database system? We query it, but the point is that when we write an SQL query, we have to write the query using the vocabulary of the logical schema. So that's the way of the data of the SQL word. So that's what we can do is only write the queries using terms, the table names and the attributes names that actually appear in the logical schema, but we cannot use any term in the conceptual schema. So this really means that in SQL systems, I cannot use table names that are not actually the one which are materialized in the logical schema. Okay, in the area of knowledge presentation, and this is where I did start 30 years ago, people did focus on conceptual schemas alone. So we developed a bunch of very expressive frameworks, logic frameworks, where we could represent knowledge and conceptual knowledge and reason about it, so that we can build the perfect conceptual schema by checking whether there is any problem, having explanation systems, checking entailments to validate to increase the trust on the system, and all these things have been done in the area of knowledge presentation. But this was completely independent on the fact that maybe we want to use this conceptual schema in a database. Of course, as I mentioned, the vocabulary in the conceptual schema may be different from the vocabulary in the logical schema. So I need mappings that connects the two. So I need also a formal connection between these two vocabularies, because the word of the conceptual schema, which is a vocabulary with its own constraints, and the word of logical schemas, which is also a vocabulary, table names and constraints also, primary keys, foreign keys, triggers, whatever you want, SQL checks and all these things, they will have, these two vocabularies have to be connected also formally. Okay. Okay, now our dream is how do we want to use conceptual schemas in databases? We want actually to query the database using the vocabulary of the conceptual schema. Say an SQL query where we actually write, use table names that come from the conceptual schema and not from the relational schema, from the logical schema. And of course, again, this has been studied holistically in knowledge presentation. So something like, okay, if we have a conceptual schema and some query expressed in this vocabulary, can I check the consistency of the query, the containment of the query, the optimization of the query, the simplification, whatever. So this has been done. But again, pretty much, I'm exaggerating because this has been the focus of the last 20 years of research of many research groups in the world. But ideally, the bigger focus has been just an holistic focus. So, so what can we do now? What we want to do? What is the goal of this kind of research? Well, ideally, we would like to find a way where, okay, yes, we write a query in this language. Okay, we write a query in this language, in the conceptual schema language. And instead of basically do the long road to get the answers, so normally basically not using at all database technology, but using ad hoc technology, to answer the query, because this would involve to use the conceptual schema knowledge, to convert it somehow, to massage it, to query somehow, to use the data which is stored in the logical schema, etc., so that I could then get back an answer. Okay, and this is, for example, what has been done in Datalog. In Datalog, we have basic facts, so a database. On top of it, we have a Datalog program which introduces new vocabulary elements, which are the head of these rules, Datalog rules, so that I can then use this as queries, so I can check what are the data which is held in these heads. And as we know, Datalog programs cannot directly use SQL technology for many reasons, complexity reasons, whatever. But the point is that, okay, we can do that, but we will lose all the efficiency and all the technology that we already have in databases. So what we want to do? What we want to do is to find a way to do a rewriting. So the rewriting is the fact that, okay, I know theoretically I want to study the problem whenever this is possible, to translate the query over that uses the vocabulary in the conceptual schema into an equivalent for some notion of equivalence. We can see that this later. In an equivalent, in quote, query that uses the database schema, the database vocabulary. Okay, so basically a pure SQL query over the database. If this translation is possible, then this means that the only cost of computational cost in this whole endeavor would be just the compilation of this query into this other query, of the original query into the compiled query, and this compilation would be as complex as it should be, but the complexity does not depend on the size of the data, which is important because we want to maintain the complexity of query answering, data complexity of query answering the same as the one of SQL systems. Okay, so let me immediately start with an example. The example involves the first sequence of examples involves the classical database setting. Okay, so suppose we have this entity relationship schema, and in this very simplified example, I assume the database is exactly stored using the same vocabulary as the conceptual schema. So what is the vocabulary here? Well, we have a unary table which are all the employees, a unary table with all the projects, a unary table with all the managers, and say a binary table for the works for relationship that connects employees and projects. Okay, so this is what I'm going to have. So I'm going to have 3 unary table and 1 binary. Okay, so in this example, I say, well, I have managers are employees, or this is, I'm using, okay, by the way, I'm using my own version of conceptual modeling language that to be neutral and not upset anybody. So this is not UML, at least for the reason that I'm using in a non-standard way the cardinality. So this is not a look-through cardinality, it's just a participation constraint. So every project has at least 1 employee working for it. Okay, so this is the meaning of this cardinality constraint. Okay, if I have this conceptual schema and have a database associated to it, so a unary table where I have all the employees, which are 3, all the managers, and all the projects. And then I have the binary table works for, which says that John works for project A and Mary works for project B. Okay, this is my example. Of course, we all know that if I have a query, something like, okay, tell me all the managers that work for some project. Okay, so this is this query is written in this. Well, it's just like a compression. Tell me all the instantiation of X such that the following open formula is satisfied. Okay, so in this particular context, the example, okay, I'm looking for all the managers. So there are 2 managers here, and John and Paul. Then John and Paul, I have to check whether they work for some project. And well, John works for a project, but Paul does not work for any project. So the manager that works for some project is only John so far. And let's check whether project A is actually a project. Well, it is a project. So yes, John is the answer of my query. Okay, nothing fancy. This is what I do. This framework can be efficiently implemented, top-down evaluation with relational algebra, whatever you can understand, because basically my query is using a vocabulary for which I know everything. So I know the exact instantiation for each single vocabulary element in this, because the database tells us. But clearly in the real world, we have a slightly more complex situation. So take this example, where now I have, again, unary table, employee and project, binary table for works for, but also binary table for name and name, which are the attributes of the project. So to understand, so John and Mary are employees, project A and project B are projects. Then John is called John, the name of John is John, and the name of Mary is Mary. And similarly, well, the project A has name project A, project B has name project B, and then of course, John works for project A, John works for project B, and Mary works for project A. So that's an example again. Okay, now if I have a conceptual schema like this, suppose this is an ER diagram, then you don't expect that the database will look like this at all. Most likely, it will look like this. So there will be a single table, a non-normalized table, a non-normal table, where you have joined all these elements. So basically, it's a table which I call the employee table, which includes would include an employee ID, the name of this employee, the project in which this employee works in, and the name of the project. So if you look at the data, really, this database down here in this unique table really corresponds to the data I have above. So John is called John, so focus on the first line. Sorry, John is called John. John works on project A, and project A is called project A. If you really look at this data here and this data here, they are really the same, well, with some provisos. So this is really the same if I have some additional information. For example, I have to know that the primary key of this table is made of these two attributes, and then there is a functional dependency. So between the project ID and the name of the project. This means, well, I may have John appearing twice here, okay? But John works for two distinct projects. Each project will have a name, but if I have, say, the same project appearing twice, I have to have the same name for it. So there is a functional dependency. Okay, so intuitively you can see that this is what will happen. So I will have this conceptual schema above. I will have this actual database below. So how do I connect these two things? Well, for making this connection, I need to introduce a notion which is lossless transformation, the notion of lossless transformation. So if I have two schema, now another thing I need to say, which is why I'm using conceptual here in parentheses, because you may be upset by my choice, in the sense you may argue that this is not a conceptual schema, while this is a conceptual schema. Well, according to my definition, they are both conceptual schema, because what is a conceptual schema is a vocabulary. And here below, I have a vocabulary that includes a table name, employee table, and 4 attribute names. And then I have constraints over these attributes, this vocabulary, sorry. I'm saying that the two attributes, employee ID and project ID, form together a primary key for the table employee table. And then there is a function dependency, so that basically project ID functionally, the project name functionally is dependent on project ID. Okay, so I have a vocabulary and constraints. So according to my terminology, this is also a conceptual schema. And this may be the right conceptual schema for the agent that wants to use optimally the information system. Remember that this is already an abstraction with respect to the actual data. In fact, the actual data in a database will be stored in a completely different way, for sure not in tabular form, okay? So I would call both conceptual schema. Having said that, that's also why I'm saying here conceptual in parentheses. Okay, having said that, I introduced the notion of lossless transformation. I have two conceptual schemas, two schemas. with different vocabularies. Remember, a schema includes a vocabulary and the constraints over this vocabulary. Now, and the fact that a vocabulary has a bunch of constraints, the schema includes the constraints, this means that the legal databases for that schema are exactly defined by these constraints. So by having two schemas, I will have two distinct sets of legal databases. So in this example, this would be one legal database, and this would be another legal database, one for the first schema and the other for the second schema. So I have two conceptual schemas, and each of these conceptual schema, I'll show you an example of a legal database for that schema, okay? But there may, as you can imagine, each of these two schemas has, once you fix the vocabulary, a very large number of legal instances. Okay, so if I have two conceptual schema with different vocabularies, we can say that one conceptual schema is the lossless transformation of the other. So we say these two schemas are equivalent. If there are two total injective mappings from all the legal databases of one schema to the two databases of the second schema, legal database of the second schema, and vice versa, so that the composition of these two injective mapping leads to the identity function. What does it mean? It means that if I have, for example, this instance, I can find a way to map this instance into an instance of the other one, and vice versa. I can map this into an instance of this. So I should be able to find these mappings. Of course, these mappings should be such that if I start with a database and I use this mapping to find the legal database of the other schema, and then I use the second mapping to come back, I should find the same database, okay? And this for any possible legal database of the two schemas. Well, this is a very strong notion. In fact, you realize, for example, that in this case, if I, for example, I don't know, delete this primary key, the fact that this attribute belongs to the primary key, I may have instances of the employee table, let's say schema, instances of this database here, legal instances, which do not map into legal instances to the other one and vice versa. So they don't find this identity. This is one case. Or for example, if I keep this one and I don't have these cardinality constraints again, which really is exactly what I'm talking about. This functional depend, this part of the key corresponds to these cardinality constraints. Okay, so it's a very strict condition that tell you that some mappings will be the right ones, but only because there are the constraints, okay? And I will show an example of the mappings in the next slide, but now suppose there is this notion. So whenever I can do that, these two schemas are equivalent, so they are lossless. The one is a loss transformation of the other and vice versa. Now, because I have these mappings that basically, because legal databases correspond to legal databases. So if I have one database if I have one database in one schema, because of the mapping, I can find the legal database in the other schema and vice versa. So this means that and if I can express these mappings as views, as first order views, so basically relational algebra transformations, then query answering, it's simple, because querying over one schema where the data is in the other schema really amounts to expand those mappings as views, okay? This notion now, this is just, I cannot really say much more today, but I will leave in the website of the EROSS series some references so that if you want to go and go deeper in this notion, you can read papers. But this notion, this formal notion of losslessness as the base of the database design, for example, well, you may have noticed, of course, that this transformation that you see in this slide is exactly the composition notion of third normal form in database design. So all the notion of transformation that I do apply to the design my optimal database from an ER schema, from a conceptual model, are necessarily lossless, because if they were not lossless, then I would design a database which does not exactly capture what I wanted to capture with my schema, conceptual schema at the beginning. It's also the base of database normalization, because database normalization is at the heart of database design. And of course, is also crucial in database reverse engineering when I do the opposite thing. I start with a database relational schema with its own constraints, and I want to get the conceptual schema out of it. Of course, the conceptual schema I get out of a reverse engineering process has to be the lossless version of the original data. Otherwise, I'm just modeling something which does not correspond to reality. Okay, in this example, if we consider these two conceptual schemas, okay, at the top and the bottom, these are the mappings. So the upper mappings are just saying, if I have a vocabulary in the lower schema, how can I get the vocabulary in the top schema? Well, I'm saying the vocabulary in the top schema corresponds to some view over the bottom schema, and vice versa. If I have the vocabulary in the top schema, how can I get data for the vocabulary of the bottom schema? Okay, I have a view here. This is the classical transformation that happens in classical decomposition in database design, but so it's a trivial example, but this gives you the gist. So these are the two mappings such that their composition gives you the identity, because the data has to satisfy the constraints imposed by the two schemas. Okay, going on. Another element which is crucial here is the notion of object identifier, because again, if I really look at this database schema, this is not really what I would ever get in a database system. I will never store object IDs. I will actually have to store the primary keys, which are in one-to-one correspondence with the object IDs I have in mind. So indeed, there is a whole theory and a particular, say, if in this context, you can see this as a specific lossless transformation, which says that under these constraints, this schema, that now what has this schema? I've added a new attribute, which is the primary key, SSN for employees and project code for projects. Now, when I transform losslessly into this other schema below, well, you see that now the object IDs, so the instances of employees, the instances of project are disappearing. They are not there anymore because, well, they are in one-to-one correspondence with their primary keys. It's more complex than this, but let's keep the intuition here. And so this is a lossless transformation. So I can go back and forth from the two schemas, from the legal instance of the two schemas, by having appropriate mappings. And now we had an entire talk a couple of weeks ago, maybe 3 weeks ago, by Terry Halpin, who was devising a much more complex way to have conceptual schema talking about identification of instances of classes. Okay, he called this reference schemes. And of course, they're not just primary keys, they become much more complex. And if you want, you can review that talk in this perspective. So what we have is that we have a conceptual schema and another schema, this relational schema below, that is completely equivalent to the above one and is perfectly computable in terms of query answering. Okay, now the point is that if you really want to go on with improve database technology, extend database technology with knowledge presentation ideas, with this ideas of having rich vocabularies, ontologies, knowledge graphs, you most likely want to go to lossy transformation. Let's see the two most remarkable cases of lossy transformation. One is the dbox case. Historically, it's the other way around. So dbox came much later. They're less important, but in terms of explanation, I think this makes easier. So what I have in a D box? Well, I have my conceptual schema. I have my legal database. Oops, but observe that employee, the vocabulary element employee is not in my, is unknown, its extension is unknown in my database. So basically the extension of my database does not include, so my database does not include any information about the employee. So I introduce the notion of incompleteness, okay? And the idea of a D box is that every element of the vocabulary either is known completely, like manager, works for, and project, or is completely unknown, like employee. Okay, still, I can answer queries here. For example, suppose I want to ask for all the employees. Now, at this point, I would ask the audience, what would be, in this particular example, the answer to the query employee? Well, we can't right now with this live meeting technology, but so I will answer for you. So if I ask for all the employees, what would be? Well, first of all the managers are employee. So if I want to know the employees, for sure, I know that the managers are employee. But also, so the manager means John and Paul. These are employees for sure, because it's manager is a subclass of employee. But also, whoever works for a project has to be an employee. John and Mary are also employees because they work for a project. So the answer would be John, Paul, and Mary. We call this the certain answer because, as opposed to classical database technology where we have the exact answer, so it's that and this is it. This is okay, for sure I know, given the information you gave me, I cannot do better than this. For sure, John, Paul, and Mary are employees. There may be more, maybe not, who knows? That's the best I can do. Now, what is interesting in this approach is that for sure, I can rewrite this query into this query. So, which exactly captured the kind of line of reasoning we had in finding who are all the employees. So what we have is all the managers, union, all the employees that work for some project, okay? Which is, now these two queries have the same answer. They're not equivalent. Well, now what is the advantage of this rewriting? Well, what we have now is that this query here includes only terms of the database. So manager, manager and works for, we know everything about it. So if we had a query, we start with a query with a term, with a vocabulary element that was not included in the database. Now we have a query which gives the same answer, which now uses only terms in the database. So that's an answer to my original question. Can we rewrite queries in a way that a query over the ontology vocabulary employee can be rewritten into a query over the database vocabulary manager and works for? So that's a positive answer to that question. Let's consider this other approach. Okay, why is this lossy? It's lossy because clearly there are legal databases of the conceptual schema and legal databases of the other schema, of the relational schema, which are not in one-to-one correspondence. Okay, another lossy case is the A-box case. So now we, in addition to the fact that some terms are not included in the vocabulary, so I don't have employee here, I only have works for and project, fine. But moreover, I have the fact that these tables, these vocabulary elements are not completely known. So I know for sure some elements, some instances of these tables, but there may be more. So they are open-ended, okay? So that's the case of an A-box. The term comes from description logic, OWL, the ontology web language. Okay, so what happens if we are in this case? Well, again, suppose I want to ask the query, tell me all the projects. I want to know all the projects such that there exists some employee working for it. Okay, again, what would be the line of reasoning here? Okay, for sure, I have to look now, because of this constraint here, I know that all the projects, for sure, all the projects I know about, I want to know, I want to know all the things for which there is somebody working for it. Okay, that's the query I want to know. There is no notion of project here. Because of this notion here, of this cardinality constraint here, I know that every project will appear necessarily in all the works for relationship, because every project will be, because of this constraint will appear in the works for, even though in the actual A box, in the actual extension of works for that I know about, there is not such a thing. Okay, so this means that even if I ask for works for, I'm using the works for query, and the works for does not include project A, does not include project B nonetheless will be in the certain answer, because necessarily every project should be appearing as a second argument of works for. Again, also in this case, this query can be translated into a query that where I can just look at the data. So give me all the project and anybody, anything that there is somebody working for it. And in this rewriting, I will consider the A box as an actual database. So I will consider the A box without this last part. Okay, this query will be just a database query over the complete data. Okay. Now, the bad news is that if I use a D box or an A box approach and I want to have an expressive conceptual modeling language, and I want to adopt certain answer semantics as we have shown, now the complexity is co-NP-hard in data complexity. So this really means this is much, much harder than database technology and cannot be reduced. In spite of the example I've just shown you, which are just simple examples, cannot always be reduced into database queries, because otherwise complexity will be much lower, sub-block space. So what can we do as a fix? People, well, having observed this, they started to look at two possible direction of fixes. One, the most popular one, vastly most popular, I believe that next week, Maurizio Lenzerini, who is going to speak at EROSS, will talk about that deeply. It's okay, if we reduce the expressivity of the conceptual modeling language we are using, and also of the query language, and we try to reduce the least we can. So let's keep as much as expressive as we can by keeping the database complexity. Then we can get rid of this high complexity and go back to the, say, SQL query complexity for data complexity. The other approach is, okay, no, I want to use expressive conceptual modeling language and expressive query languages, but I'm going to focus only to specific class of queries which may belong to this whole language, which are called determined queries. So basically, the queries for which you can reduce the approach to a lossless via lossless transformation. Now, again, it's quite detailed. But again, this is another approach which is the research on this area has been just started, and there are no practical tools on this, while in OBDA is plenty of very effective tools. And again, I guess Maurizio will talk about this next week. Okay, so we have bad news, we have fixes, which I don't want to talk about, but there are more bad news, which basically depend, for example, on the fact that we adopt certain answer semantics. So no matter about the complexity that we may achieve and having an ideal complexity, data complexity, we still have, may have sort of philosophical issues here. So let me talk about issues that may arise when you adopt these powerful approaches where you can have ontologies that, so what is the approach? Now maybe this has to be clarified. So why do we want to have these lossy approaches? Well, because really we want to use the most expressive, the best ontology we can have, where the vocabulary is very rich, right? And so these are not necessarily match exactly the data that we have. And this is the approach of knowledge graph, for example. And this is the approach of OWL. So we have some data, we have a generic ontology about a particular domain, we have some data, and then we connect the two, but the ontology may be heavily detached from the actual essence of my database, so there will be a lossy transformation. There may be incompleteness, for example. Again, I believe that Maurizio will talk about this, or maybe not, I know. But the point is that incompleteness, the idea of using A-box semantics for your data, it may be crucial in data integration settings, because basically when I have data integration, when I integrate two distinct sources of data, the integrated version may necessarily include incompleteness. And so we have to deal with these things. So having these things is important, but we have to be aware that when we adopt these approaches, some other things follow. For example, this. If we adopt certain answer semantics, well, let's make the simplest example I could imagine. Managers are employees. I know everything about managers. I don't know anything about employees, okay? Okay, then let me ask about all the employees. Okay, what is the certain answer? Well, in this very simple, trivial setting, we know the certain answer is John and Paul. So because employees, I don't know anything about that. The only thing I know is that they are a superclass of managers. Well, for sure, the best I can say is that whoever I know is a manager is also an employee. So I will say, well, John and Paul are employees because John and Paul are managers. Okay, fair enough. We know that. Sounds cool. However, this question may arise. Are managers and employees the same conceptually? Because they behave exactly the same way. So they are the same extension in this context. Okay. And of course, we know that this is not really true that they have the same extension. However, if I query my system, I will get the same answer. In fact, there are a way to understand whether they have the same extension. I can check whether, well, let's look whether George is a manager or whether George is an employee. Well, if I ask whether George is a manager, the answer is no, George is definitely not a manager. I can definitely prove that because I have the exact extension of all the managers. Okay, now I ask about, so false. I ask about employees, but I know employees also, if the certain answer for employees, the certain extension of employees includes John and Paul and nobody else. So if I ask whether George is an employee, should I get that this is not the case? Well, no. What I get is I don't know, because George may be an employee. The employee class is a superclass of the manager class. So John and Paul are managers. John and Paul are certainly employees. That may be more. Who knows? I don't really know in my world whether this is true or not. So this is fine. We know that. But what is the practical consequence of this? That I cannot cache the answer. I cannot materialize answers that I get while querying my system, so that I can use these answers, these materialized answers as views, say, for subsequent queries. And this will be evident with another example that I will show you later. Okay, let me show another problematic case. So, well, problematic again. So I would not say problematic. I would say something that you should know that happens while you adopt certain semantics, for example. Here, something that you should know that happens while adopting A-box semantics. Okay, suppose you have this conceptual schema, and then suppose that there is an entity which is defined by a rule, by a view. Okay, so could be an OCL view, could be an SQL check constraint, could be a trigger. And this says, well, look, in my database system, the bad projects are exactly, it's a view, right? It's a rule. The projects such that nobody works for it. Okay, so they're the bad projects. Okay, nobody works for this project. So it's a subclass of project. Fine. Okay. Now suppose that I treat my database as a dbox, and in a case, so as a database, as a dbox in one case, and as an a-box in the other case. So the data is the same. Okay, data is the same. I have the fact that John works for project A and Mary works for project A, and project A and project B are project. In one case, I have my I have the fact that I know exactly my tables. In the second case, I have an open-ended view of this, so it's an a-box. Okay, if I now query the bad projects, well, in the dbox approach, well, who are the bad projects? Well, I check, I use the definition. So these are all the projects, which namely project A and project B, but I have to leave away from these the projects that have a person working for it. So project A has 2 persons working for it, fine. So I'll leave them out. So what is left is project B, fine. But what if now I ask the same query, bad project, in an a-box semantics? Well, because there is this open-ended here, I don't know whether there is somebody working for project B. So project B may have somebody working for project B. So the certain answer is the empty answer. So again, I get, in spite of the fact that in my data, I don't have anybody working for project B, I would not get this in the answer, which is fine because this is what the semantics says, so it's not an error, right? However, this is incompatible with the same view if this view were expressed in my database system, or even worse, in my code. Okay. Okay, I see that I cannot show you the last slide. Okay, because it's time to finish. So I wanted to talk about another issue about compositionality, which is lost if I use certain answers, but that's it's in the slides. Okay, so my conclusion is very, very simple. I don't want really to say everything again, but I want just to say that if you want to connect conceptual schemas to databases, ontologies to databases, knowledge graphs to databases, and you want to do it properly, satisfying somehow the exact meaning of what a database is, well, my message of this talk is they have to pay attention. And this is it. Thank you.
Thanks a lot, Enrico. You got me curious. I was going to ask you to go back to that missing slide.
Okay.
Now I want to know what's in it.
Okay, let me just show you the complete slide here. Okay. Okay, the missing slide says, if I have, well, usual case, I have a conceptual schema, I have a database, let's say, interpreted as an a-box. Okay, so I know something. I know something about works for and about project. Okay, now I have my query, and I want to study the notion of compositionality of query. In order to study the notion of compositionality of query, I have to use an algebra. So I cannot use somehow this first order way of representing queries. I will use, let me use in green, I will use a relational algebra way of writing queries. So this is really, these 2 queries are the same. It says, tell me all the projects such that there is at least somebody working for it. We already seen this query before, right? Now, the problem is that if I evaluate this query, okay, I get, as we have seen before, the answer project A and project B, because there is this cardinality constraint here. Okay. This cardinality constraint here enforces the fact that also project B, even though it's not in the list of works for, is also among the projects such that there is at least somebody working for it. But if I decide to evaluate the query in steps, if I first evaluate the works for subquery, well, project B is not there. Okay, so when then I take the projection, I will get only project A. So I lose compositionality of query whenever my query language is going to be compositional, like relational algebra. That's something that you have to pay attention to. Again, this probably means that if you have this query written in your code, for example, as you have a loop in your Java program that expands, that basically, for example, computes the scan of your database, then this loop will become invalid, right? Because this loop, that really would be this one. If you implement this in your Java program or whatever, then this will not be the same as evaluating the query as a whole. Again, something to pay attention to, nothing fancy. So this is the way it should be. Just pay attention, which is really the message of my talk.